Okay, here we are, lecture 23. We're talking about minor losses, and the objectives of this lesson are to evaluate minor losses for hydraulic systems, which basically means can we solve for them, and then we're going to combine the friction losses, which is what we were working on last week, with the minor losses to solve problems. So basically, this is the apex of the course. So you can do the problems here. You've pretty much gotten out of this class what you're supposed to get out of it. Sorry about the squeakiness in my chair. I'll try not to adjust so much. The way we start this is really with just this idea of a minor loss. Okay, so I'm gonna talk for a little bit, and then we'll kind of get into it. So this is the energy associated with viscous dissipation of turbulence. Okay, and that's fairly complicated, but it's not really something we're going to get too much into at bends, fittings, valves, etc. Okay, so basically, anytime there is a change in the pipe. Okay, so if the pipe gets thinner or fatter, or it goes through, let's suppose you have two pipes and you kind of put them in a little shorter, like a fitting, like a little shorter, bigger pipe to hold them together, or anything like that. Basically, there's going to be like a sudden loss of energy right there. If it turns, anything that is unusual. So as far as like the along, so like if the pipe is really long like this, all along this pipe, we've got friction losses all along here, right? But if all of a sudden, like, I really don't know how to draw it, but like right in here, let's suppose somebody put a valve, right? And so usually they draw them something like this. So you can imagine this is something where you turn this top thing and that opens or closes this valve, right? And so we're losing energy all along here, due to friction, but right here by this valve, okay, we're gonna lose a lot more energy, okay, or per unit length anyway. So, we might be cruising along, losing some amount of energy, and then we hit this valve, and then we're going to lose something when we get to that valve, and then we're going to continue downwards. Okay, so that's the idea. This is the EGL. Okay, so anytime there's a valve, a fitting, if this pipe were to bend, anything that might happen, if there was a bend right here, there would be a loss right here. Okay, if really anything that could possibly happen. If this pipe ended and there was another pipe right here. So it's kind of like an irregularity right there. So there would be a minor loss here as well. Okay, and so they call these minor losses. And the reason they call it minor loss, and I think we're going to see this in a second, is that in the grand scheme of things, per unit length, this is a lot more than, say, what's going on right here, right, or right here. But usually over the length of the entire pipe, these losses are much more, okay, much greater than these. So these are typically called minor. And this, like friction loss, is usually called friction loss. I don't think I've ever seen it called major loss, but I don't see why you couldn't call it major loss. I've just never seen it done. So it might even, for all I know, it might be done that way. Okay, so that's what it is, physically. Mathematically, what it is we get HL, so that's the head loss, equals HF plus H lowercase l. Now again, this is just the nomenclature of your book. Other books are going to use something else. But this is the minor loss, okay? So this guy is the minor loss, okay? And really, and I mentioned this, I think, briefly in last class, really for the system or, for your control volume, you can kind of put a little summation sign there, okay? That's not official. I've never seen it written that way, but that is the correct way. Now, people do put that in later on after they start working through a problem, but basically you want to add up all of the losses in the system. Get your head loss. Okay, so for a given, in my notes I say for a given fitting, I guess we'll go with that. But for giving fitting / bend / whatever called I, the head loss for that thing is pretty easy actually. It's K sub I times V squared on 2G. V squared on 2G. Okay, so basically, to get this, you just need to know what this guy is right here, this K. Okay, so once you get that, assuming you know what the velocity is. So it was going to depend kind of on what type of problem it is, type 1, type 2, type 3. But this is really how you get this. And so this K comes from a chart. Okay, so for example, and this is really how this is usually done. So this is from your textbook. I don't remember what the chart is. But if you're working a problem, you know, and I mean, this is obviously not an exhaustive list. I mean, they do all of this experimentally to figure out what these values are, you know, but so if you've got a pipe entrance, you know, so if you're like right in this top group right here, and you've got a pipe entrance, okay, so the head loss is K, E, okay, so the K for the entrance, V squared over 2G. Now, what I want to point out to you is which V do we use? So in this case, you have to look at this figure and you can see that the V is the one that is in the pipe. Okay, it's not the one out here, which, so it is not this V, okay, or not that V, however you want to say it, okay? And then the key parameter here is, for this one, is R over D. So what is the radius of curvature here of this bend divided by the diameter of the pipe, okay? And that would tell you, you know, if you knew those two quantities, if the coefficient was 0.1 or 0.2. I mean, I guess technically this, obviously based on that greater than sign, it can go bigger than that. Okay, so you know, similarly, you know, these get fairly complicated. Let me zoom in on a few. We're going to talk about the expansion specifically in a second, so I'm not gonna do that one. I'll zoom in a little bit. No, I gotta sit up. Sorry, that's making too much noise for you guys. Let me. Okay, so if we look at the expansion, then what's important, well, there's two things. It's the angle of the expansion and the ratio of the diameters. Okay, and so that's, you know, that's a little frustrating, okay, because obviously there really should be an entire chart just dedicated to this. But in this class, we've really only got a theta, you know, two possible angles, 180, okay, which would be when it does this. Okay, so that would be a theta is 180. Okay, and then 20, which is more like what they've drawn in their picture. And then it's just d1 over d2. So if you have d1 over d2, so the ratio is, you know, 0.6, well then, and it's 180 degrees, well then that's your K value. Okay, now you might get a little worried, because and this does happen quite a bit, but what happens if we've got d1 over d2 as a half? So if d1 is like 1 meter and d2 is 2 meters. Okay, so d1 divided by d2 in that case, d1 over d2 would be 0.5. Okay, well there is no 0.5, it's right in here, 0.5. Okay, in that case what you need to do is you need to linearly interpolate, you know, between these values. Okay, so that's halfway between 0.4 and 0.6. So your value, let's suppose we had a theta of 0.20, so your value is going to be halfway between these two. Okay, so in that case, it's going to be 0.20. Okay, now you might ask, well, okay, well that's great, but what if I get a value that is, you know, what if d1 over d2 is like 0.22, right? So it's not halfway in between, 0.22. So, I mean, obviously that would be pretty weird, but it could happen. Okay, so it's somewhere in there, and it's obviously going to be closer to this value, which means over here it's going to be closer to that value. But we can't exactly figure out what it is. So what we need to do is we need to linearly interpolate. So basically we kind of need to figure out the percent this is between these two. Okay, so what we're going to do is we're going to set up a proportion, because we want to figure out a number over here that is the same proportion, x, between these two. Okay, so what we're going to do is we're going to say, okay, 0.22 minus 0.20. So that's the distance between our 0.22 and the 0.20. Divided by the total distance between these two. Okay, 0.40 minus 0.20. Okay, so that'll give me the percent of the total distance between those two that 0.22 is from 0.20. Okay, so now I'm going to use that same sort of ratio, that same sort of logic over here. Okay, so the large value here is 0.04, so the large value over here is 0.25. Okay, so the total range over here, minus 0.30, okay? And then over here, you know, this is where our value is that we're looking for, x, okay, minus 0.30, okay? And so it's just doing proportions. Okay, and we could solve that in this case, and we get x equals, 0.295. Okay, and that would be our K. Okay, I called it X, but we should have called it K. Okay, so that's how we would do it if we were stuck there. And that's just annoying, but you're going to basically linearly interpolate. Okay, so that's the, if you need help with it, you may ask me, but if you want to look on the internet, type in linear interpolation. Okay, I remember that really threw me for a loop. You're basically taking a straight line approximation between these two values. If you need to ask me about it, it's fine. We can talk about it. Just ask me. It's not going to show up very much in this class. So then, of course, we have these special kind of bends. This is a miter bend. And the miter bend, what they do is they put in these little veins that help guide the water as it makes that turn. I'll go ahead and erase those. I shouldn't have kind of drawn there. Okay, but you can see those veins kind of guide the water around that turn. And the purpose of those veins is to reduce the loss that you might find in that 90-degree bend. More common, is a smooth bend. Okay, so if you can create a smooth bend like we have here, then what you're going to find is that your coefficient of loss is going to be smaller, which is usually desirable. I'm sure there are moments when people don't want their losses to be smaller. I can't imagine what they are, but you can see them right here. And so what's going on here is, again, it's just radius divided by diameter. Okay, and then the last thing is at the bottom here, and there's huge listings of these valves and fittings and things like that, and you can find these all over the internet, and they're much more comprehensive than what your book is using right here. But they've got all the different types of valves. For your homework or anything like that, I would use ones that come off of here. On a test, if I used one that was not on here, I would give you one to give you the K value. But like you can see, okay, you've got a globe valve, okay, and it's wide open. Well, here's the K value. I don't even know what a return bend is, but if I told you had a return bend, well, there would be that K value in there. Okay, 90-degree elbow. Okay, well, there's your K value. Okay, so, I didn't line that up very well. Okay, this is your K value. Sorry, this is not your K value. Anyway, so there's a K value for pretty much everything that happens. Okay, and so let's back up a little bit and let's talk about how well these work, because they're really approximations. So if we zoom over here, okay, and let's suppose I'm going to zoom in like right over here. Let's consider this particular example here, where we've got an expansion. And so, and the reason we're working on this is because we have already done this one. And we're never going to do it the way that we did it initially. But we'll talk about that in a second. But basically, this expansion is 180 degrees. Okay, so in essence, what's going on here is, it's not really as it's drawn. So it's drawn kind of the way you would find it in that diagram. But in reality, what's going on is it's kind of going like this, and it's splitting out wide as it comes through here. Okay, and for this thing, I forgot to give one given, but d1 over d2 equals 1/5. Okay, so that's, obviously it's kind of important information because it really matters. Okay, so the way we would do this now, if we wanted to solve this, luckily it's fairly easy, is we go back to that equation that I just put down like, a slide or two ago, and I would say HL for this fitting, okay, so we'll call this fitting 1, okay, equals K for that fitting, 1, times V squared onto G. Now, there's a few questions that we need to figure out here before we solve this. And one of them is, and this is kind of the most important one, is that V, we have a V1 here and we've got a V2 here. And we know that V2 is going to be less than V1 because it's, it's a larger diameter, right? But we don't know which one is going to go right here, okay? And so for this, what we're going to do is we're going to refer to our chart. So stay with me for 1 second. I'm going to zoom over there. Okay, so we're going to zoom down here. Okay, here's an expansion. Here's the expansion I'm going to erase for a second. All right, so here's our expansion. And we've got d1 over d2, okay, is 1 over 5, so that's 0.2. Okay, and we've got an angle theta of 180 degrees. So that means K is 0.87. Okay, so that's the value we want right there. Okay, because that's the K that gives us, and that's the D1 over D2. Now, the other thing that's important, though, is it tells us right here that the head loss is based on V1, whereas V1 is the entrance. Okay, so we're going to use 0.87 V1 squared. Okay, so we're going to go up here. Okay, so it's just, you just got to pay attention to the to what's going on with the you know, with what the chart tells you. So HL1 for that fitting, okay, or that expansion in this case, is 0.87 times V1 squared on 2G. Okay, so that would be how you would solve it, right? If you knew V1, you could just plug it in, plug and chug, boom, got it. Okay, so let's compare that to how we've been doing this. Okay, so in you know, with the momentum example, momentum equation example, or you know, whatever you might want to do it. So the way we've been doing this the whole time, and you know, I haven't really made you do it that much, but still is, and this would give you the exact answer. Okay, as if we did this. Okay, divided by 2G. So if we did that, okay. Now this of course leads us to, we've got two velocities here, and you're like, whoa, 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 we only had one velocity up here, right? So how do we solve this with, or one velocity that went into the answer, right? So to compare these two, we have to recognize that those velocities are not independent. They do depend on each other. So I can recognize that V1A1, so this is an aside. Okay, we're going to do some continuity. V1A1 equals V2A2. Okay, so let's see. We want this in terms of V1. So I'm going to say that V2 equals V1A1 divided by A2. Okay, and then we kind of need to deal with these areas. So let's just keep going. Equals V1 times pi D1 squared over pi D2 squared. Okay, so V2 equals V1 times, divided by 4 on top and bottom. Okay, divided by 4, divided by 4. Okay, that all cancels anyway. So we're left with D1 over D2. Let's stop being crazy here. Squared. Okay, and the ratio of D1 over D2 is 0.2. So if we plug that in, equals V1 times 0.2 squared. So V2 equals 0.04 V1. Okay, so we can plug that in here and we can solve. Okay, so we'll go ahead and do that. HL equals V1 minus 0.04 V1. Okay, squared on 2G. And with a little bit of simplification, we can show that this becomes 0.922 V1 squared on 2G. Okay, so that's the exact answer. Okay, or really it's kind of like the theoretical answer. And this is the answer, this is the empirical. Okay, the empirical is probably better. I can't tell you why they're different. I don't know anything about these experiments, but this is the way we're going to be doing it moving forward. It's also easier, so that's very beneficial. Okay, so this is the way we're going to do it from going forward, so don't worry about trying to memorize this particular formula or how to do this. Okay, this is the way we're going to do it. Okay, that's the winner. Okay, that's the chicken dinner right there. Chicken dinner. Okay, winner, winner. Okay, so now I'm going to work, in two problems. The second one is a barn burner. Probably harder than anything, definitely harder than anything I would ask you to do on a test, but it's going to demonstrate all of the concepts of everything from this class. Although it's either type 1, type 2, or type 3, so obviously it doesn't demonstrate the other two, but it's the ultimate expression, or the ultimate difficulty level for an energy problem. Okay, so without going too far into it, let's do the next problem, the easier one. All right, so let's zoom over. Okay, and there it is. All right, so here we go. So it's given the flow rate. We're given that this is oil. It's kind of weird. Somebody has 2 reservoirs of oil that they're moving stuff from, but I guess it's probably not unprecedented or anything. It's we could just. So I guess it's hard for me to think of oil as being open to the atmosphere like this, but I guess you never know. So anyway, we know the flow rate in cubic meters per second. We know this is oil. We know 2 things about the oil. We know the viscosity. Again, remember that this is a viscosity. It is not a V, so it's a little, kind of curvy V. We know the specific weight, and we know that this is a smooth pipe. Okay, the smooth pipe, on some level, you might be like, okay, cool, smooth, which means I don't have to look something up in a chart, but it usually is harder. Okay, and we'll get into that in a second, but it makes reading the Moody diagram a little bit more difficult because you don't really have a flat line. But so, if we think about our typical tools, in light of what we're looking for here, and what we're looking for here is the elevation of this first reservoir. Okay, so if we think about our typical tools, like momentum is out, okay? We don't have anything to do with forces. We don't have anything to do with, we don't have anything to do with forces on the moving fluid, so momentum is out. Okay, continuity in geometry, obviously these two are going to come in. There's no hydrostatics either because there's everywhere in this thing the fluid is moving except in the two reservoirs, which are uninteresting. So what we want to do is I'm going to focus on this energy equation because, it just seems likely that that's what we're going to kind of be driving at, right? Because what's happening here logistically is that we've got energy here, okay, in the form of elevation, and it's being converted. It's, some of it's being lost, the elevation head's being lost. And on the way, down here at 2, we only have elevation. Okay, so this is all we have here is elevation. Okay, but it's like elevation probably of 130 feet, and elevation at 1 is going to be something higher. So we've lost that energy. Okay, we don't have any velocity head down here. We don't have a lot, we don't really have anything. So it just went elevation from one to another, but there was loss. We lost energy as it flowed down this pipe due to friction and due to losses in those expansions and not expansions, in those bends and in the exit. Okay, and the way that I solved this one, and I don't really know why I did this, but we are going to ignore the entrance and the exit. Okay, so this guy right here and this one right here, we're going to ignore. And I think that the reason we're ignoring this case, I'll be more explicit on a test, but the reason we're going to ignore these is because we don't have any information about them. Obviously, we could rework this and I could give you information about them, but we're going to ignore them. And instead, the only minor losses that we're going to include are going to be this bend and this bend right here. There's 2 of them. Okay, so let's start with the energy equation and let's just see how this works out. Okay, so if we look at this, and we're gonna just kind of like walk through and get rid of terms. Okay, pressure 1 and pressure 2, these are both atmospheric. Okay, atmospheric. Okay, so those go away. Okay, Z1 is what we're looking for, so this gets a beautiful question mark. Okay, there's no Z2 is 130. Again, you could make that 0 if you wanted to, but then your answer for Z1 would be relative to Z2 instead of, relative to the elevation, which is what the question was. It was the elevation, okay? Neither location 1 or location 2 have any velocity because of the tank assumption. Okay, the tank assumption. Okay, there's no pump, there's no turbine. There is head loss, however. So this is going to be split up into HF plus HL. Okay, so this is about kind of what I just described. So this elevation minus 130 meters. Okay, so I just moved this to the other side of the equation. Equals the head loss. Okay, HF plus HL. Okay, and so that's that makes logical sense. But we need to now get at those terms. Okay, so this is pretty powerful, pretty important logistically to think about what's going on. And so Z1 minus 130 meters equals, okay, HF. Well, that's F L on D V squared on 2G. And HL, well, based on what we just said, that's going to be the summation of the Ks times V squared on 2G. Now, we don't know which V, right? So I'm going to put I here, and we're going to be summing over the I's. Okay? So that's kind of important. Well, it's really important. Now, this V right here, for the pipe, that refers to the velocity in the pipe. Okay, so that should be a little P right there. Okay, because that's where the energy is being lost. Logically, it seems reasonable to expect that these two might end up being the same thing. But let's go ahead and check it out. Okay, so sliding over here, we can look at this this chart again, okay? And we want to note that we're dealing with 90-degree bends, and there are two of them. They're the same in our problem. And R over D, which is given, okay, is 2. So the coefficient of loss is B, okay? And notice that, well, it doesn't even say anything about which velocity we're talking about, so it has to just be the velocity in the pipe. Okay, so this is the V in the pipe. Okay, so there we go. There's our head loss, 0.19 velocity in the pipe squared over 2g for both of them, okay, or for each of them if you want to look at it that way. I think that's the better way to say it. So let's zoom back over, okay? So we're going to zoom back over here, okay? And we will note that, I guess I'll make sure we can still see the whole problem. So we'll know that this V over here is also the V in the pipe. So now we're sitting here, and basically we know what this K is. Okay, we know it's 0.19, and we know I've got 2 of those. What do we need, I guess, in order to solve this? Well, we need the velocity in the pipe for both of these locations. We have the L and then we have the D. We need this F. Okay, so basically we need VP and we need the F. Okay, so we're just gonna really quickly, I'm not even gonna spend any time on this. We're gonna solve for the velocity in the pipe from continuity. So here I've solved for both the velocity in the pipe using continuity, and just because I think it's gonna be useful, I've gone ahead and solved for the velocity head. So now the last thing that we need is to get F. Okay, so this F right here. Okay, and so we'll need to go to the Moody diagram, which is right here. You didn't see it, but this is the 8th time I've tried to get it to show up. So, all right. So to get the Moody diagram here, we're going to need 2 things, okay, in order to get our F, right? We need to know the relative roughness, which is best if you have the pencil tool if you're trying to underline things. But we need to know the relative roughness, and we need to know the Reynolds number. Okay, and the relative roughness, luckily for us, well, or unluckily ultimately, but is easy because they told us this is a smooth pipe. Okay, and there's an area for smooth pipes. There's a line for smooth pipes. So I'll go ahead and I'm going to go ahead and trace that line as best I can. Obviously, it's not going to be perfect. So there's the smooth pipes line. Okay, so the reason that is kind of the hardest one is because it's got a slope on it, which means it's usually kind of the hardest to read. If we were up here, it's pretty easy to, not screw that up, okay? Because almost no matter what Reynolds number you get, you're going to get the same value of F. The smooth pipe, that is definitely not the case. So we need to make sure that we're getting this Reynolds number correctly. So to solve for that Reynolds number, we're going to plug in numbers of, so our velocity, which is 1.5845 cubic meters per second, okay, times the diameter of the pipe, which is 0.15 meters. Okay, and then we're going to divide that by the viscosity of the oil, which is given as 10 to the minus 5 meters squared per second. Okay, so our Reynolds number, 2.4 times 10 to the 4th. Okay, so that's, ultimately pretty low, but, that's a 4. Okay, but not so low as to be, as to not be turbulent. So we don't really need to worry about that. Okay, so 2.4 times 10 to the 4th. Okay, so here's 2 times 10 to the 4th. Here's 4. Here's 3. So it's somewhere in the middle here. So I'll go ahead and trace this with, red. And we're just going to kind of go straight up from there. Like to there or so. And then we're going to bounce over to the left. And we're just going to do the best we can. And it's obviously not going to be perfect. And don't stress out about that too much, okay? So 0.00 or 0.024 is what we're going to use, okay? So that's what we're going to use for F, okay? So in case you were wondering, this is a type 1 problem, okay, in case you were wondering. And we didn't even think about what the types were, but we didn't need to iterate, and so that was the key, okay? And the key was, in this case, we didn't know what the head loss was, okay? So, so we'll go over here, and we can use that value. And so now we have everything we want. So I'm going to do, so we have everything at this point, right? So we've got F, we've got the velocity head in the pipe, Okay, and we've got these K values. Okay, so algebraically, I'm going to work this, I'm going to kind of just do one little quick algebraic thing, which you will see from time to time. If there's a single pipe, what you will see a lot of times is people will rearrange this algebraically, just because, I don't know, it makes sense to them. But if there's a single pipe, okay, you may write it as this plus the summations of the K's, okay, times V squared on 2G. Okay, and you can only do that if it's a single pipe, right? Because obviously if the V squared, the V is not constant because the pipes are changing diameter or something like that, this is not going to work. But this is the way you'll often see this written. And so, I'm just gonna kind of follow that convention. Because it illustrates that ultimately we're just adding up all of the head losses, okay, to get the total head loss. So minus 130 meters equals F is 0.024. The length of the pipe, the total length of the pipe, if we refer to our original diagram, 60 plus 7 is 67 plus 130 is 197 meters. Okay, divided by the width of the pipe, which is 0.15 meters. Okay, plus, okay, the sum of the K's. Well, we've got two of those bends, so two of them at 0.19, that's our K. Okay, so all of this times our velocity head, which is 0.12796 meters. Okay, we can solve that, and Z1 is 134.08 meters. And since I only want 3 sig figs, we'll say 134 meters. Okay, so that's it's pretty solid. It's a solid problem all around. This one would make a great test question. Okay, something like this easily could show up. In fact, this would be, if I only get to ask you one energy question on the final, you should be thankful if you get this one, because this one's easy, because there was no iteration, there was nothing like totally weird like that. Okay, so in a second, or let's forget in a second, let's just go do the doozy. All right, so let's go to the doozy. And it doesn't really look all that bad, although it does look big by comparison to what I just did. Okay, so, all right, so what we've got here is, really not that scary looking, but it quickly kind of will blow up on you. But I think what's important here is that what I want you to do is I just want you to be able to think through this, okay? And so first things, okay, so we've got a reservoir on the left, and it's draining to the reservoir on the right. We've solved problems like this numerous times in numerous different ways. It's a very common way to draw these problems. In fact, the last problem was pretty much like this. The difference in this case is that we've got lots of different losses. So I've got a loss at A, an entrance loss. So we're actually going to evaluate all of the losses. So there's not going to be any that I magically ignore because I don't feel like it or whatever. So we have to deal with losses in A, lowercase b, and lowercase c. Okay, we also have to deal with friction losses along the walls of pipe uppercase A and pipe uppercase B. Okay, so that's a lot of losses. Okay, that's 5 total losses. So you can kind of imagine that head loss term being split out into 5 different things. And then there's the last thing about this, which, so what they're saying is that if the elevation of the surface of the water in the first reservoir is 60 feet higher than the reservoir in the second reservoir, 60 feet. So if there's 60 feet elevation difference between the two reservoirs, what's going to be the flow rate between them? Okay. And one of the tricky things here that you probably haven't realized yet, because I don't think you've done that homework yet, is that this means that this is a type 2 problem, okay? Which means there's going to be iteration. So if it's type 2 or type 3, you're going to have to iterate. So if you're either looking for Q or if you're looking for D, okay, you're going to have to iterate. And so you have to kind of prepare yourself mentally for that possibility. But there's other problems here that I guess we'll just get into. And let's start by looking at our tools, okay? And first of all, obviously we have 2 pipes of different diameters, so it seems highly likely that we're going to need this continuity. Okay, the geometry is going to come into it, but it's going to come into it kind of subtly. you know, like this 60, you know, that's geometry, but, you know, it's not terribly, you know, complicated or anything. There's no hydrostatics in this, just because there's no manometers, nothing, you know, nothing, at least nothing obvious, anyway. So we're gonna cross that out. And again, momentum, we have nothing with moving forces, forces on moving fluids. So this energy equation is gonna kind of be our bread and butter here. So let's just go get it. Anyway, so here's our energy equation. And fortunately or unfortunately, you know, the first starting point with the energy equation is a lot of times not as, you know, difficult, you know, or it's fortunate that it's not difficult, but it's unfortunate that there are things that are more difficult than the energy equation. Okay, so let's start going. We're gonna define our points here. This is gonna be 1. This is gonna be 2. Okay, so our control volume is everything from 1 to 2, which means between 1 and 2, there's no pump, there's no turbine. Okay, the pressure at 1, atmospheric. Pressure at 2, atmospheric. Okay, Z1 and Z2. Well, we don't know what they are, but we know Z1 is 60 feet above Z2. Okay, and then due to the tank assumption, V1 and V2 are both 0. Okay, boom, right, nailed, right? We're already moved beyond the energy equation. This problem is easy. Wagner, you lied to us. 60 feet equals the head loss. Boom. That's like not only is the problem easy, but like that's like the simplest solution ever. Okay, right. Yeah, great. You know, I wish that were true. Okay. So let's keep going. You know, as you listen to me laugh with maniacal glee at the misery that we're about to get into. All right, so 60 feet equals the friction loss plus the minor losses. Okay, and so that's how we're going to kind of split this thing out. Okay, and I'm going to actually do those kind of separately because this is going to get really ugly. I want to make one note here real quick before we continue because I'm gonna do another aside over here. Is that this Q over here means that VA and VB are both unknown. Okay, so that's 2 unknowns. We're gonna real quick do continuity just so we have one fewer unknown. Okay, we're basically gonna put one of these in terms of the other just because that's gonna make our lives easier. Okay, so let's do that right now. So we're gonna scroll over here, and I'm gonna do as an aside. Okay, I'm gonna do continuity. Okay, so there it is. I just did the continuity. Okay, so the flow rate in A equals the flow rate in B. Okay, and if you plug in the diameters and whatnot, you'll end up getting VA is 4 VB, or in this case, for whatever reason, when I solved this the first time, I made it a quarter of VA. So it looks like everything's going to be solved in terms of VA instead of VB. It doesn't really matter. So we're going to move on. And what I'm going to do at this point is I'm going to focus on these terms separately. Okay, so the first term I want to focus on is I'm going to focus on this term. So I'm going to go over here and I'm going to do that. Okay, so that the minor losses. Okay, so if we keep in mind where our picture are, so that's going to be at lowercase a, lowercase b, lowercase c. So those are well, 2 of them are expansions and 1 of them is an entrance. Okay, so it's going to be HL equals. Okay, so at A, we're going to have V something over 2G, some V squared over 2G. Okay, and then at B, we're going to have, something going to be times a V squared on 2G. Now, I don't know which V that is, and I don't know the number that's going to go out in front. Okay, so I'm kind of leaving those open for now. And then we're going to have a V squared on 2G. And again, so what we're missing right now is we're missing, these coefficients, these Ks. And we are missing, kind of like what is the subscript that's going to go right here? Because that's going to tell us which velocity we're working with. Okay? So let's analyze each of these in turn. So what we're going to do is we're going to use that chart up there on the upper left, and I'm going to have to zoom way in, give me 1 second and we'll do that. So we're going to go up here. Oh, keep in mind, and this is a little bit weird, but all the angles here are either 90 degrees or 180. So that means like this is a 180, this is a 180, and you can think of this as two 90s right here. Okay, so it's just kind of a way to, you know, they're all sharp bends, I guess is what it boils down to. Okay, so if we zoom all the way in up here, okay, and we want to look at that entrance. Okay, so this is A right here. We're going to deal with A. Okay, it's an entrance, so the flow is entering the pipe. Okay, so we're going to go up here. Here's our pipe entrance right there, right here. Okay, and let's see if we can't figure this out. Okay, if the angle on the pipe is 180 degrees, okay, then that means the radius of that bend, it's like that. There is no radius, right? There is no radius. Radius equals 0. Okay, so that's this. Radius over diameter is right there. Okay, so our K in that case is 0.50. And the velocity that we need is the velocity in the pipe. So in our problem, that's VA. Okay, so let's zoom back out. Okay. And we can go over here. I'm going to put 0.5. And I'm going to erase this. And I'm going to make that, well, if it will allow me to write, I'm going to make this VA squared. Okay? So that's the first one. Okay, the second one, okay, now we're going to look at B right here. Okay? And we'll note that, sorry, you're hearing the puppies having a dream. It's pretty funny, actually. So at part B, we've got an expansion. It's 180 degrees from a 1-inch pipe to a 2-inch pipe. So let's go up here and see what that tells us. Okay, so here's an expansion. Okay, and D1 over D2 is right here. So here's our expansions. Here's our theta is 180, so we're going to be over here. Okay, D1 over D2 is a half, so we're going to be right in here, 0.5, halfway in between, which means we're going to be halfway in between these two right here. Okay, so halfway between 0.70 and 0.41 is, well, when I solved this, I did 0.56, okay, which isn't exact. I wonder why I did it like that. We're just going to go with it. Obviously, you'd be better off if it was 0.555, but, you know, it's just what happened this time. Okay, so we're going to use that, and notice that the velocity that they use here, V1 squared. So in our case, that's the first pipe that it starts in, so that's VA. Okay, so we're going to go back here, go all the way down here, and this will be 0.56, and this one right here, if they'll let me erase it. They do not want to let me erase it. By they, I mean I'm screwing up. Okay, there you go. Okay, so this one is also going to be VA. Please let me get the pen that I want. You are a jerk computer. All right, so then for C, this is an exit. Okay, so exits are actually really nice and easy because there's only one velocity, so it's going to be B, and the coefficient is going to be 1 because you lose all of that. You lose all of that momentum. You know, all that velocity. The velocity head basically gets lost as it exits. But let's just go ahead and we can ascertain that over here. We're going to treat that like it's an expansion, okay? And it's really a special expansion, okay? So theta equals 180, and D1 over D2. Well, D1 in this case is the pipe, which has a diameter of 2 inches, but D2 is a tank. So basically D2 is infinite, okay? So this ratio basically goes to 0, okay, which means we're going to use 1.0, okay? So that's kind of how you do this. So 2 inches over infinity is 0, okay? So we're going to use 0 in this case. Oh, and the only velocity in this case that even exists is the first one, but it tells you that right here, V1, okay? So let's go back over here, and we will plug that right in over here. So this is going to be 1.0. And we're going to make this VB, okay? Now remember in this case, because that's going from pipe B into the tank, okay? So I really want to erase that. That's very sloppy right now. Okay, so let's, I guess I'll do that in blue. Okay, VB. Okay, so there you go. There's our head loss, right? And you're like, okay, well, that's cool. It's a little messy. Let's just do a little algebra on that, and just to kind of clean it up. You can kind of see how this is not very helpful, because what we're looking for is Q. And we've got this terms of VA and VB. Now we've got a little continuity over here, so we can get rid of one of those VAs or VBs. But it's not really helping us solve the problem. I don't know. We'll see. Let's just see what happens, okay? So I'm going to do HL, and that's 1.06 times VA squared on 2G plus 1.0 times VB squared on 2G, okay? And if I plug this in there, okay, and square it and do all that business, I'm going to get that HL equals 0.017. Now it's got units, seconds on feet squared, okay, times VA squared. Okay, so that is one part of our energy equation. Okay, so we've got one part right here. What about the HF? Okay, well, the HF is the other part. So let's maybe we'll do this one in blue. So we'll look here. I guess I should have planned this out a little better, but we can go over here. And the total HF is, we need to add it up for both of the pipes. So HF equals, for the first pipe, FA, LA, DA, VA squared on 2G, plus FB, LB, DB, VB squared on 2G. Okay, I think, maybe you're looking at this now and you're going, okay, I could see how this is starting to get a little bit complicated. Problem being, of course, these F's have to come off the Moody diagram, and there's two of them, and they aren't the same. And that's kind of the rub, right? So let's see how we can simplify this. Okay, and so what we can do is we can plug in the numbers that we know. Okay, so LA, if we kind of zoom out a little bit, LA is 20 feet. Okay, so we've got 20 feet divided by DA, which is like super tiny, right? Because it's 1/12 of a foot, right? And then we're going to do 1 divided by 2G. So that's going to be 64.4 feet per second squared. Okay. And then that's going to leave FA VA squared. Okay, so that's the first term. And then we're going to kind of follow the same pattern for the second one. We'll do LB, which is 20 feet, divided by its diameter, which is going to be 2/12 of a foot. Okay, and then we're going to multiply that by 1 over 2G, which is 64.4 feet per second squared. I apologize for my sloppiness. Let's kind of get some space here. Come on. Okay, 64.4 feet per second squared, okay, times FB VB squared. Okay, so, all right, well, let's simplify this a little bit, and we'll get HF equals 3.727. It's got units, seconds per second squared per foot. Okay, FA VA squared plus 1.863, same unit, second squared per foot, FB on VB squared. Okay, now once again, we don't like working with both VA and VB, so what we're going to do is we're going to take continuity, and I'm going to plug it in for VB. Okay, and if you square it and you do all of that, we end up with HF equals 3.727 seconds squared per foot, FA VA squared, plus 0.1164 seconds squared per foot. Okay, let's put that in parentheses. FB VA squared. Okay, so now we've got two things. So this is these are the friction losses over here. Okay, and they are a function of the friction factors in the pipes and the velocities in the pipes, although we've made it only a function of one of the velocities because they depend on each other. And in the meantime, over here, we've got the minor losses. Okay, and so this is from all three of the changes in the flow conditions. Okay, so fittings and bends and all those things, expansions. Okay, so we're going to combine these two back into our energy equation. Luckily, combining them back together is not really difficult, but you can see that the equation that it's going to create is kind of disgusting. Okay, so let's go back to white. Okay, so get back to our energy equation, and we'll say 60 feet equals 0.017 seconds per foot squared VA squared plus, and I'm going to rearrange this a little bit, FA times 3.727 VA squared plus FB times 0.1164 VA squared. Okay, so ugly, very, very, very ugly. Okay. Now note, first of all, if we knew the velocity, we'd be done, right? The big problem here is we don't know the F's. Okay, so let's stare. I mean, I taught this last class, but I want to talk through it again. So let me bring out the Moody diagram so we can talk about how to get F. So let's go look at Moody over here. We're going to kind of zoom in, and I want to think about, how we get F in the context of this problem. And what it boils down to is, to get F, you need two things. You need the relative roughness and you need the Reynolds number. So when we think about the relative roughness, the problem in this case is we have two different pipes and they have different relative roughnesses, but we can solve for them. Okay, so epsilon in pipe A, okay, the relative roughness of both pipes, they're both made of the same material, whatever it is. They, the KS, the sand roughness length for each of these is 0.00015 feet divided by, for A, it's 1/12 of a foot pipe. Okay, so if we divide that out, we get 0.00180. Okay, so that's relative roughness of pipe A. Okay, notice we had to convert because we wanted it to be unitless. If we do it for B, I could say, well, epsilon B is, well, it's the same roughness elements on the pipe itself, but it's 2/12. So it's it's twice as thick of a pipe. So sure enough, the relative roughness is half. Okay, so there you go. So those are our two relative roughnesses, and and so that part's fairly straightforward. That's one of the nice things about being a type 2 instead of a type 3. Type 3, neither axis is easy. So what we're going to do here is epsilon A, so 0.0018, so 2 zeros and then 1/8, so maybe we're like right here, more or less. And so I'm going to kind of trace that line, just so we'll kind of be able to work with that. Now again, it's not going to be perfect. Just do the best you can. Okay, so that's about where we're looking, okay, more or less. And then for B, and of course we're hoping that the Reynolds numbers will be high enough that we don't have to deal with the left-hand side of this graph. Okay, for B, let's see, so we've got 3 zeros and a 9. So that luckily should be fairly easy to trace because it's between the 0.01 and 0.0008. So we're right in here. Okay, unfortunately this blue color is very similar to the blue that's on their graph, but I think it should still stand out enough that you can see it. Okay, so just right between those two, okay? And so that's what we've got. So this is B right here, and this one right here is A. Okay, so, okay, good, great. But the problem is, we don't know the Reynolds number, and the reason we don't know the Reynolds number is because we don't know V, right? So VD on nu, okay? And we don't know V, so we can't get that. So what we're going to do, but if we did know that, we could get an F, okay? So if we knew this, if this were known, then F would be known, right? So the idea here, again, this is that circular logic, is that we're going to guess an f. Well, actually, we're going to guess two f's up here. Okay, once we guess those f's, okay, we can solve for this v. Okay, once we solve for that v, we can take that v and use it to solve for the Reynolds number. Once we have the Reynolds number, we can get the f over here, right? And that can become our guess. Well, it's actually going to be two guesses, okay, up here. And we're just going to kind of keep doing that circular logic until it converges, okay? So we're actually going to do it now. So I'm going to erase all these squiggles that I just did. But that's the concept. And if it doesn't make sense, then we can just, follow along, and hopefully it will make more sense as we do it. Okay, so we're going to be careful here. Okay, so before I get there, I'm going to title my my equations. This is my first equation, okay? And so what we're going to imagine is we're going to guess f's, right? And they're going to go into this first equation, and they're going to pull out my VA, right? Once they pull out my VA, then I'm going to say, okay, well, that's cool. I got my VA. But now I want to get my Reynolds number. So what I want to do is I want to come up with equation 2, which is going to help me get my Reynolds number, okay? So equation 2, well, I'll put the final version of it here. Over here, we'll just kind of do it as an aside. And we'll say that the Reynolds number in A equals VA times dA over nu. Okay, so VA is unknown, so put that over here. dA is 1 over 12 in feet, and the viscosity is given as 1.11 times 10 to the minus 5th feet squared per second. Okay, so we can plug all that in, and yields 7507.5 times VA. Okay, so actually I shouldn't do that as an arrow, should I? That's kind of an arrow. Okay, usually the arrow should mean you're going to the next line. Some of you kind of use it as a replacement for a equal sign, and it doesn't mean that. Okay, so I mean, so we're going to do the same thing for the Reynolds number here for B. So dB over nu. Plug in the values here, except we'll have 2 over 12 feet VB over 1/11 times 10 to the minus 5 feet squared per second. And we'll get the Reynolds number equals 15,015 VB. Again, the significant digits on Reynolds numbers is not really clear to me that it's necessary to go out this far. But again, this whole problem we're solving it in terms of VA. So we're just going to go ahead and convert this to a VA equation, in which case the Reynolds number is 3753.8 VA. Okay, so good. So now we've got our second equation, which is really a double equation, okay? But it will help us moving forward, okay? And then that will be our strategy. So basically the strategy is going to be, okay, so if I kind of have all of this here, is that I'm going to guess F, okay? F, guess, or a lot of times you use assumed, okay? And there's going to be 1 for A, and there's going to be 1 for B, okay? Then from equation 1, I can get the velocities from equation 1, okay? And basically what I'm going to be getting is, I'm solving for VA, right? And VB is really coming from continuity, okay? So basically I take VA and I just divide it by 4, multiply by a quarter, and you'll get B. And then from there I can get the Reynolds number, okay, using those second equations, okay? And then using Moody, once I have Reynolds number, I can go ahead and get my F's, okay? And that is the fundamental way that a type 2 problem is solved. Okay, so all of these are A and B, and A and B. And again, we're just going to keep going until these converge. Okay, now, so we have to get to what's our first guess right here. What is our first guess? Okay, and I'm going to do these in colors. I'm going to try to color code this. I always try and I always kind of fail. But let's just see what we can do. So let's zoom in here. And we've already marked where these epsilons are. Okay, we've got A and B. And what I want to kind of point out here is that the best first guess for B is, if I kind of draw this line as best I can along here, kind of a dotted line, right, if I can do it. Okay, is maybe a little bit below 0.20. The best line for A, okay, again, let's use the flat part if we can. Again, I didn't do a great job drawing that flat part. Okay, so maybe it's right up in there. Okay, so it's maybe 0.022. Okay, so either one of those are both good guesses. What I'm going to do, just because it's the way I did it when I first worked this problem, those are fine if you wanted to use 0.022 and 0.19 or 195 even for B. You could do that. The way I did this when I first worked this, though, is I assumed that for A, which is in green, I just made them the same. The reason being, this just made my life a little easier, right? It is, you know, I figured that I'm only going to have to iterate this once, probably, as long as I have a good guess, and those are both perfectly reasonable guesses. So I figured that I could just, you know, that those would be fine. And it's just going to make my life easier if they're the same. Okay, so once we do those, we're going to plug both of those values. Maybe I'll use red to kind of show you the path. So those are going to go up into here and here. Okay, and from that I can solve for VA right here. Okay, and if I do that for VA, I get 25.22. And VB from continuity, which we did way back when up here, okay, basically I divide that by 4, and I get 6.31. Okay, note this is in feet per second. FPS, okay, feet per second. Okay, so then I'm going to plug those values in, or really I'm going to plug the A value in here and here, and get my Reynolds numbers. Okay, so A is going to be, well, B is 9.5 times 10 to the 4th, and A is 1.9, is 1.9 times 10 to the 5th. Okay, and then we're going to go to Moody, right? So let's go on up to Moody. Okay, this is the first iteration. And let's keep our Reynolds numbers in sight. Let's not get out of hand here. And so we'll start with 1.9 times 10 to the 5th. So here's 10 to the 5th right here. Here's 2 times 10 to the 5th. So 1.9 is just a midge over here. And we're on pipe A, so we're going to go up until we reach the A line. So maybe like right there. And then I'm going to bounce to the left. Okay, so let's see if we can't figure out where that puts us. Okay, so that looks like it's about 0.023 maybe. When I first did this, I got 0.024. So we're gonna go with that because I don't want to redo this. Okay, so when I first did this, I got 0.024. So we're just going to assume that that's the answer. Notice those differences off by 1/1000th, or really the second significant digit, don't really matter. Actually, if you stare in right here, you can see that I turned a little early. So my first guess was probably better, although they're probably both fine. All right, anyway, so Reynolds number for the second one, 9.5 times 10 to the 4th. So here's 10 to the 4th. Here's 2, 4, 6, 8, 9, and 10. So somewhere in between those two is 9.5 times 10 to the 4th. So we're going to go right up to there. Okay, and we're going to hit our blue line. And well, it looks like we're almost going to get the same value, almost. So let's draw that one like that. Okay, and I'm going to use the value that I did again the first time I did this, which looks pretty close to what I got this time, 0.022. Okay, so we can plug these in over here. So we'll say 0.022, and this one is 0.024. Okay, so those are our guesses for the next time through this equation. So 0.024, and this one is 0.022. And right now we're hoping that we get the same values here because we don't want to do this again, right? Because this is not enjoyable. Okay, so again, we're going to follow the same thing. We're going to plug both of those into equation 1 to get our VA. And this time we get 23.41. And for VB, we'd use continuity, and we're going to divide that by 4, and we get 5.85. Notice these numbers really aren't that different, so we may be good. There's no real telling for sure. To get this absolutely correctly, you would use a computer, but right now, so if we plug those into the Reynolds number equations, equation 2, we're going to end up with 1.8 times 10 to the 5th. Okay, you should be seeing already that that's going to be hard for me to parse on the Moody diagram. And then this is going to be 8.8 times 10 to the 4th. Okay, and so if I go up to the Moody diagram, let's see if we can even see how much these Reynolds numbers have moved. Maybe I don't really have another color. I wish I could tell it to draw and dotted for me. But let's start with the green. So let's start with A, 1.8 times 10 to the 5th. So here's 10 to the 5th. Here's 2 times 10 to the 5th. So 1.8, we're like you probably can't even tell that I'm drawing right there. Maybe if they'll let me have black. They won't really let me have black. I'll just do red, So, it's so close that you can't even tell the difference, right? So we end up with the same value for that one. And then for this one, so 8.8 times 10 to the 4th. So now we're at, so we're probably here. Again, it's so close that we're not really going to be able to tell the difference. And that's what you're looking for, okay? Are these absolutely 100% the correct answers? No, you're going to need a computer to get it more exact than that. But you've got the first significant digit unquestionably. It's definitely 0.02. And the next digit is either, for this one, the next digit is either a 1, 2, or a 3. A 2 is a good guess. And for the next one, this one's either a 3, 4, or 5. It's a very good guess. Okay, very strong. If you change them, if you notice, the velocities don't change all that much. Okay, so notice comparing them to these answers, to our first guesses, the velocities change, but not really so much that we really worry about it. Okay, so to finish this monster of a problem, what we would do is we would say that Q equals either one of these. We'll use this one, VA, AA. Okay. So that's 23.41 feet per second times AA, which is going to be pi times the diameter, which is 1/12 of a foot squared, divided by 4. Okay, so Q equals, sorry, the dog is whimpering in the background, 0.128 CFS. Okay? Cool. Okay, now before I let you go, the last kind of thought process in this whole thing, if we zoom in, granted, yes, that is a doozy, but if we zoom all the way in, I just wanted to think real quick, because guaranteed on the final, there will be an Hdl, Egl. So I want to go ahead and draw those real quick, because we've done all of the head losses here. I could even back out and quantify them very easy because I've already worked them all. But I'm just going to kind of do them, qualitatively. Okay, so we've got a little loss right here. We've got a little loss right here. We're losing energy faster in A than we are in B, so it'll be kind of steeper. Okay, there'll be a little loss right here, and then it'll be less steep for the remainder there. Okay, and so that's the way that we're losing energy in this problem. And I'm going to assign you guys probably an extra EGL, HGL one, because I know that, you didn't really, we didn't really get to do a lot. And the problem that I gave you, well, I like it because it's easy to grade. It's, It doesn't really make you think all that much. I guess it makes you think. It's a good question. All right, anyway, so that's the EGL. That's what our energy is doing. So as we cruise along, every time we hit a place where there's a minor loss, there's a little tick downwards, okay? That's a minor loss, minor loss, minor loss, okay? And then everywhere else, we're just slowly losing energy as we move down the pipe, okay? And the narrower the pipe or the rougher the pipe, the steeper the line because we lose energy a little faster. Okay, now if I do the HDL, okay, remember the difference between the HDL and the EGL, the HDL equals the EGL minus V squared on 2G. Okay, so it's going to be below the EGL, so it's coming along here. They're together. It's going to be below the EGL by, okay, and parallel here because the pipe has the same diameter. So this is VA on 2G. Okay. And then when it hits here, we know that it's going to be VB on 2G, but they're away. Okay, noting that VB on 2 squared on G on 2G is much smaller. Okay, in fact, it's actually going to be 1/16 as big, so I didn't even draw it to scale, right? Because the velocity is 1/4. Okay, so that's what it looks like. And so there's a massive increase in pressure right here. P on gamma goes through the roof right here, okay, because the velocity, because it slows down in pipe B. Okay, so that's all I got for today. Take care of yourselves, and I will talk to some of you tomorrow or soon or whatever. And I'm gonna post I'm gonna work the final in video format. If you want to watch that, I don't know how long that'll be a long video. I'm sure maybe I'll break it up into a couple. So that'll be posted soon, probably tomorrow. So anyway, hope y'all are good and take care of yourselves. And I'm here for you. All right, take it easy. Bye. K value. Okay, and that's much more is